Now we're going to talk about the FranckCondon principle and finish up electronic transitions. So you know that electronic energies and states are independent of the nuclear motion. This is from the Born-Oppenheimer approximation. Think rhinos and mosquitoes. What that does is it allows us to have transitions that couple with vibration, kind of. You'll see what I mean. All right, so you're happy with this, hopefully. E1, E2, E3. So if the are actually, so this is n equals 1, n equals 2, n equals 3. These are electronic states. Okay, and so what we want to do is we want to include, so you've seen this hopefully where you've got an electron, photon comes in, and then it then jumps up to a higher energy level. Okay, so if we take this, and I could say that this is an S1 and this is S2, and it's jumping to a next higher energy level. Vibrational and rotational energy transitions, which you've just spent a crap ton of time working on, reside within here. So if I took this and took this line and put it on a plot where I'm looking at internuclear distance, such that 0 at this plot is going to be that the atoms are overlapping with each other. If I took this line and put it onto this plot where this is my energy, I would get something that looks like this. Look familiar? That's the Morse potential. This line and this whole thing represents an electronic energy state. And I'll go ahead and add some. So these are my vibrational modes. If, however, I have, so this is S1, if I now have another electronic energy state, it's going to look something like this. So now I've got, so this represents this line, this one represents that line. So if I have an electron going from this state to this state, I'm actually having it go from one of these rotational and vibrational states up to another set of either rotational or vibrational within the electronic. Cool? Because if you think about it, UV vis, IR, they're not that far apart on the electromagnetic spectrum. So there is going to be some coupling and overlap, and that overlap occurs when you've got certain states having certain vibrational energies within electronic, and then it jumps up to the higher states. Okay, so what does this all mean? Well, the FranckCondon principle says, actually I'm going to pause and write it on the board and then read it to you. FranckCondon. It says, electronic transitions occur much faster than the nuclei can adjust to a new equilibrium position in the excited state. So I have for you this picture. Let me move this. So, well, never mind. Hopefully you can see it and the reflection's not causing trouble. Okay, so I've got, here's my energy, here's my lower electronic state, my higher electronic state, and I've got my vibrational modes tucked within. Now don't forget, I also have rotational modes in here. I'll make them better spaced. So my rotational modes are also in here. The rotational coupling we're not going to go in that far into detail. So we really only care about the electronic and the vibrational relationship. Okay, so electronic transitions occur much faster than the nuclei can adjust. Think about on this plot what it means for the nuclei to adjust. What does it mean to adjust? So if you go to a higher energy state, so there's R, if you go to a higher energy state, say, so the electrons existing in some sigma orbital in the middle, if you go to a higher energy state, now you're going to have a different electronic potential between these two nuclei, and what that does, if you change your potential having a higher energy state here, that means that you've got new potential. The only way to satisfy this equation is to have a new wave function, which means your electrons are going to cause this separation to now adjust. And so most likely your excited electronic state is going to have, so if this is your equilibrium position, is going to have a slightly larger equilibrium position. Okay, so what happens is then upon the excitation, the electron moves so much faster than the nuclei can respond, and it's only when it's in the electronic excited energy state after a little bit of time that you have the new equilibrium position emerge of the two nuclei spacing out a little bit. Okay, so let's dive in a little bit deeper into how a transition actually occurs. So if we remember from, so this is the V equals 1, V equals 2, V equals 3. This is exaggerated just so you can see the differences. I have a plot that I will show you in just a second. V equals 1, V equals 2, V equals 3. Again, so this is simplified, but it gives you the idea. So based on the harmonic oscillator, the wave function at V equals 1 would look something like this for V equals 2, for V equals 3. All right, so I can draw the exact same thing, V equals 1, V equals 2, V equals 3. So notice I've got 1 max, 2 max, 3 max for 1, 2, 3 respectively. Okay, what this means, FranckCondon principle, means that when you have a jump from electronic state here to here upon photon absorption, you go from this line to this line. Well, the only way you can go from this line to this line is if you transfer to the most similar vibrational state. Okay, so if you're in the ground vibrational state in the ground electronic state, what's going to happen is the electron is going to go up to the state that best matches this vibrational state. It doesn't want to put any more energy in from the incident photon to changing its vibrational state. It doesn't want to do that. So it's going to go to the one that's the most similar in vibrational states, which, if the future equilibrium distance is not the same, so basically this one's going to go straight up. And I didn't draw it that well, but for all intents and purposes, let's say there we go. That the vibrational state V equals 3 is the one that best matches the peak here. So that peak and that peak are the most similar. So because the electronic transitions occur much faster than the nuclei can adjust to the new equilibrium position, it's not going to adjust such that this max and this max overlap with this lowest vibrational mode, which is the highest probability of the state that your that your lower state electron is in. It's going to then go up to the state that best matches it. Go team. Once it does that, then it's going to want to decay because this is unstable. And so instead of decaying straight back down, as in this picture, that was a lie. Sorry, that doesn't happen. But that's okay. Instead of going up and then coming immediately back down, what happens, I don't have another bulb. So, black marker. What happens then is there's going to be a decay back down, and I'm going to make this non-radiative decay to a lower vibrational state, non-radiative decay to a lower vibrational state, and then it's going to decay from this vibrational state downward. That's where fluorescence happens. If you've ever wondered why we can't just flip absorption and fluorescence, and why we have two different instruments and spend a crap ton of money to buy both, this is why. Because of the FranckCondon principle. Thanks, Franck and Condon. So electronic transitions occur much faster than the nuclei can adjust, which causes this additional non-radiative decay is what this is called. Okay. Go team. I'm going to pause, and so hopefully this makes sense. I'm going to jump to, actually, hang on. So the electron, so once it's in this excited energy state, then now it's long enough time has passed that you can then have a transition. So if you think about the transition times, Think about the frequency associated with this. Whoops. So frequency is inverse seconds. If you convert that to a time, basically take the inverse of that, that's the lifetime associated with these things. 10 to the 14th, 10 to the minus 14 is the frequency, or sorry, 10 to the 14th hertz is the frequency associated with electronic transitions. I believe it's in like the femtosecond scale. That's really fast. It's much faster than vibrations. Okay, and so because it's so much faster than vibrations, once it's in the excited electronic state, then the nuclei can adjust. So the delay for this is a little bit. Go team, which is also recognized in the Born-Oppenheimer approximation because you can separate out those two energies, which is good for us. Okay, the last thing I want to talk about with this picture is how do you calculate it? So we know that there has to be a transition dipole moment for this transition to occur. Oops. So we've got psi final. So here we've got psi final, that one, mu psi initial, that one, d tau. Okay. So in this case, our transition dipole moment is equal to the so dipole moment, charge across a distance. So this is the electronic charge times the radius from within this molecule. So the internuclear distance. Plus, now you have the charge multiplied by the proton times the radius of each particular nuclei. So if you have multiple nuclei, the radius of that nuclei to nuclei. Whereas this is the radius from the electron to the particular internuclear distance that it's, oh my gosh, R. Okay, hopefully that made sense. So then what happens, so when I take this, stick it into my transition dipole moment operator, a bunch of constants come out, which is fantastic, and I'm left with mu final initial, so this is my transition dipole moment, minus E, the sum of psi, the electron final, R psi electron initial, d tau multiplied by psi vibrational final star psi vibrational initial d tau. Go team. So these are multiplied by each other because each of these has both the wave function of the electronic and the vibrational. But this won't operate on the vibrational. It'll only operate on the electronic because these vibrationals aren't dependent on this R. They're dependent on the potential energy that they are in. I'll say that one more time. These vibrational modes are not dependent on R. They are dependent on the energy potential well, or the Morse potential that they are in, caused by the boundary conditions set by the nuclei. So this isn't operated on by R. So much like a constant, it kind of comes out, but it is known as the FranckCondon factor. Okay, so this is the FranckCondon factor. And of course, we give it a fancy name, S, B, F, B initial, squared, because we're going to square things. And that is essentially the transition intensity. Whew. This is really cool. This makes me so excited. Transition intensity. Think about what that means. This wave function multiplied by this wave function, and not just that lobe. Okay. Think about it. When you have psi A, psi B, d tau, if I said the word orthogonal, what does that do? Goes to zero. No overlap whatsoever. If, however, my vibrational wave functions have overlap, i.e., if there's a really good overlap at all, you're going to have a high number. Well, if you have a high number, you have a high transition intensity, cool, which means you have a high FranckCondon factor, which means you've got this transition going from electronic state to electronic state being that much more because the FranckCondon principle or FranckCondon factor is much higher. Wicked cool. I'm going to pause and share screen because I've got some more data to show you.